In this video, we'll be talking about our second rigid transformation, which is reflecting graphs. So first of all, a reflection is a mirror image of a graph across an axis. Since there's two different axes, we can actually get two different reflections. There's a reflection in the x-axis. To reflect across the x-axis, we throw a negative on the outside. So that would be some g of x equals negative f of x. But we can also reflect in the y-axis, which would be throwing a negative on the inside. So negative f of negative x. For example, if we had f of x equals x to the fourth, that actually looks about like this. It's like a really flattened out parabola. Let's write an equation for the function represented by this graph then. Well, this graph looks a lot like this graph, except that it's been shifted over by 1, 2, 3 units. So shifted left by 3 units. And it's also been reflected across the x-axis. Across x-axis. Well, that means that it should be, if we build this, we should have f of x. This, the left by 3 units would be an x plus 3. But then it's reflected across the x-axis, so that means we put a negative on the front. Or, if you prefer, what would that be, plugging that into this function? That would be negative x plus 3 to the fourth. So now let's do some examples similar to what we did in the last section. So let's compare the graph of each of the following functions, which are transformations of f of x equals the square root of x. So here we have the function, the square root of x in each one of these, okay? The square root function. Here, what does this do? Well, this is a reflection, and because this is negative g of x, that's a reflection in the negative on the outside, so x-axis. Over here, what is this one? So what would that look like? A reflection in the x-axis flips the graph this way. So this would be the new graph. There, and then, yeah. So we just mirror image it. So this graph right here is the new graph. Over here, h of x we see is actually negative. Here we see that h of x is a g of negative x. Well, that means that it's a reflection in the y-axis. In other words, to get the new graph, we reflect that across that way. So, like so. This would be our new function. Okay. Finally, over here, how do we get our new function? We get our new function by, so this we see is actually, we see k of x is, it looks a lot like f of x, but a 2 has been added on the inside, and we've applied a negative to the outside. What would that mean? Well, adding the 2 on the inside, so here it's helpful to see order of operations. So first, it appears that we added the 2, and then we reflected the graph across the x-axis. So we added 2 on the inside. That would be a shift left, 2. And then we also reflect in x-axis. So when we do that, we shift it left by 2, and then we reflect in the x-axis. So that point gets moved there. And then we reflect, so this goes down here, and 1, 2, 3, 4. Hey, cool. We actually get far enough to graph a new point. It is worth noting here that if you were to pick points on these, you could still do that by picking points. This just helps speed up your graphing a lot. and it helps to build some intuition in your mind about what these functions actually look like as well. So, as such, let's go ahead and have you try an example. Compare each of the following functions with the graph of f of x equals the square root of x minus 1, which I've provided for you. So, on the count of 3, I'll reveal the answer. 1, 2, 3. So here we see that we reflect in the x-axis to get the new graph. Here we first have to reflect in the y-axis, so that would send the graph to look like here. That whole graph gets flipped, so it gets sent over here. And then we shift right by 1. It's important to note that you need to get the order of operations straight, because if we had shifted it right by 1 and then reflected, we would have gotten over here. And this basically comes down to the fact that the negative in the order of operations, the multiplication by the negative happens before we do a subtraction, because multiplication is higher in order of operations than addition. So, in other words, just keep that in mind, that order of operations really does matter here. As a brief closing note, it is important to note that when we transform a function, both the domain, because of horizontal shifts and reflections across the y-axis, and the range from vertical shifts and reflections in the x-axis could change. For instance, if you look back at the example that I did earlier, you know, of course, that the domain of square root of x is 0 to infinity, and its range is 0 to infinity. However, once we reflect it, the domain doesn't change, but now if you look at the new function, its range will be negative infinity to 0. Effectively, what we did is we flipped the entire range. Here, the domain gets flipped in this one, so negative infinity to 0. But the range stays the same, 0 to infinity. In this example, we actually add 2, so the domain gets shifted up. Originally, the domain was 0 to infinity, but now it's going to be shifted backwards by 2. So, minus 2 to infinity because of the left shift. And here, the reflection flips the range. So if you look back at those graphs, you'll be able to see that these are the domains and ranges of them. Okay, but there is definitely sort of an intuition of kind of seeing how the transformations would change it just on their own. For more practice in working with both types of rigid transformations, be sure to see the book and see the following problems on pages 72 and 73 of the textbook. In our next video, we'll finish talking about function transformations by talking about the non-rigid transformation of scaling.